Everybody to our next lesson, which is on even, odd, and inverse functions. We're going to talk about even functions first. Even functions are functions that are symmetric about the y-axis. Visually, if you want to take a look over here, right, you notice that we have our y-axis running vertically, and something that would be considered even would have the same distance on either side of that y-axis. So this point right here, let's say that it's so many units away on this side of the y-axis, it would have to be the same number of units on the other side. And we would want that throughout the entire function. How we can check to see if a function is even is with this formula right here, right? If we can plug in the opposite value of x and come out with f of x, or the same function that we started with, then the function is even. So let's take a look at an example. Okay, we have f of x equals 2x to the second power. Is this even? So what we're going to do is we're going to plug in opposite of x. So we have 2 times the opposite of x squared. If we square what we would consider negative x, we end up getting positive x back. And whatever that value is going to be to the second power. We're still multiplying by 2 in the front, so this is what we end up with. This expression is the exact same as what we started with, same power and everything. So this, in fact, matches, so we would say yes, this is even. Our second example, if we evaluate at opposite of x, here we would have negative 5 times the opposite of x. So negative times a negative, that gives us positive 5x plus 1. Now here's the difference. Right here we have a positive value. When we started, we had a negative value. That means that they don't match. They're not even. So our answer here would be no, or not even. Oops, not even. Graphically, again, we just want to check, is the distance on either side of the y-axis equal to points on the function? Okay, so if I were to look at this function, right, here at a height, whatever that height happens to be on y, if I go to the left, I hit a point. That distance, if I were to go on the other side of the y-axis, that same distance, I should hit a point. But do I? No. There's nothing here. So that means that it's not symmetric about the y-axis, making this not even. Okay. On this particular example, here I can check some lower, right? And that little distance matches on the other side of the y-axis. If I check to here, it seems to be equal on both sides of the y. I can check all sorts of points, right? This distance matches this distance over here. Okay, so we can see that we would have yes, even. Okay, so we have some problems for you to try out. Take a second to pause the video and try each problem and resume it afterwards to check your solutions. Alright, let's see how you did with these. Hopefully you remember some of these older functions from earlier in this unit. Here, if we substitute in the opposite of x, we're going to have the absolute value of negative x. Now, the absolute value and that negative, they're going to cancel each other out. We're going to end up having the absolute value of x plus 2, which is exactly what we started with. So you'd want to say yes, this is even. Our second example, if we substitute in, oops, this is g, opposite of x, we would have the opposite of x squared minus the opposite of x. When we square this, it becomes positive. Here we have a double negative, so that becomes plus x. That's where we have a difference in our original. This is not even. And final one, this is going by the graph. Okay, if we check out all points left and right, we notice that we have the same distance going. Okay, so we would say yes, even. Hopefully you did alright with those ones. We're going to move on now to odd functions. Odd functions are going to be functions that are symmetric about the origin. Now, this is a little bit different than symmetric about an axis, because that's a regular reflection that we'd be looking at. Here we're looking more at like a rotation, right? If I were to take something from this whole side, right, all of this stuff on this side, and we were to rotate it 180 degrees around the origin, would it match? So we're looking at something like this point. If I rotate it 180 degrees, it should match on the other side. Okay, same idea with all these points. If we go around 180 degrees, do we match? Okay, so that's what we want to check as far as odd functions go. What you'll probably see me do is I will be doing distances above and below the x-axis. Okay, so I'll be checking, right? I know that getting closer to the origin, we have some points above. I want to make sure that I have that same thing happening only on the negative side. Okay, same idea with the extremities. Here it's on the negatives, so I know it should be on the positives. Okay, so there's two different ways that you can check with your graph. If we want to look for the formula, though, what we'd be checking is if we multiply the entire function by negative, or change all the signs, is that equal to evaluating the function at opposite of x. One of the reasons why I teach odd functions after even is because a lot of times the questions will ask you to determine if it's odd or even. So if we start with evens, which make us check this anyways, then we can use that solution to check for odd. So to me it makes more sense to do evens first, because we're doing that work anyways in order to check for odd. Okay, but these problems right now, they're just going to ask, is the function odd? So we're going to have to do both the work anyways. Okay, so let's check it out. What we're going to be doing here is plugging in the opposite of x to start. So we have 2 times opposite of x to the third minus the opposite of x. That's going to give us, well, we've got a negative to the third, so it's going to remain negative. And here we have a double negative, that's going to give us plus. So that's what we came up with. Okay. Now we want to check if we multiply f of x times -1. Basically change all the signs. Will it match with what we just came up with? So let's distribute. That's going to give me -2x to the third, and the double negative is going to give me plus x. Now I compare. I have -2x to the third, and I have plus x. Those two happen to match. That means yes, this function is odd. I'm going to move to our next example. Very similar. I'm going to plug in opposite of x to start. So we have 5 times opposite of x squared plus 8. If I square a negative, that becomes positive. So 5x squared plus 8. Now I had to get that anyways, because now I need to check what happens if I multiply the whole thing by a -1. So I took my original function, I'm multiplying by a -1. I have to distribute this. we're going to end up with negative 5x squared minus 8. When I compare those two results, they don't match. That means this is not odd. Graphically, two ways we can look at this. I think, to me, the easier way is if I look here, I notice I have a little bump above y and a little bit taller of a bump below y. And that should repeat, but the opposite on the other side. Right? So before it was below y, I need it to be above y, and I need it to be taller, which we have. And then we want it to be below the line, not y. I've been saying y. I should be saying x. Okay. The other thing that we can check too is the points themselves. If I were to take this point and rotate 180 degrees, do I match with a point that would be rotated? Okay, so that's another way that we can check the same thing. Right, if I rotate this point 180 degrees, do we come up with a point on the other side? And we in fact do. Okay, so there's two different ways that we can check a function, if it's odd or not. So now we're going to check this function right here. Is this one odd or not? Here, if I use my line test that I've been doing, right, I notice that on this side, everything is above the x-axis. So that means that on the other side of the origin, everything should be below the x-axis. But when I look down here, I don't have anything below the x-axis. That's a problem because it's supposed to be down there. So is this odd? We would say no, not odd. Okay, and again, if we were to look at the 180 test, right, if I took a point here and I rotated 180, which is a straight line, do I come up with anything? Still no. Okay, so here's some problems for you to try algebraically to test if the function is odd or not. Try them out, pause the video, resume when you're ready to check your solutions. Alright, let's see how you did with these. So we know that we need to do the opposite of x first. So we have opposite of x over 1 plus opposite of x squared. That's opposite of x over 1 plus x squared. That's the first part. We now have to check if we do the opposite of all of f of x. I'm going to take this negative, I'm going to distribute it just to the top. We don't want to do to both the top and the bottom. The reason why I chose the top is because I'm looking at my other side. I want the negative on the top, not the bottom. So that's what I'm going to do. I have opposite of x over 1 plus x squared. Now I can see that these two match, and I can say that yes, this is odd. The other problem, if we do the opposite of x, we're going to get x squared. Here we're going to end up with minus x and minus 3. What we want to compare it to is the inverse of g of x. Oh, I'm sorry, not the inverse, the opposite, rather, of all of g of x. Means I'm going to have to distribute this negative sign. If I distribute the negative sign, we get negative x squared, which I can already see is a problem. Minus x and plus 3, again, another problem. So just right off the bat, looking at the negative and positive x squareds, that's not going to be good. This is not odd. How did you do with those? Hopefully you did them better than what I had said verbally, right? I know I said a couple of incorrect grammatical things there. Anyways, let's move on. we gotta now talk about inverse functions. Inverse. Just getting a little ahead of myself. So, first, when it comes to inverse functions, we're going to talk about how to find them. We'll go into detail as far as what inverse functions are in class. As far as what we're doing here in this video, we just want to talk about how to find the inverse. So this is what we're going to do. It's a pretty easy four-step process. First, we're going to replace f of x with y. Really simple. You literally just change your f of x to a y. Our second step is we're going to replace all of our x's and our y's. So if we have multiple x's in a problem, we're going to end up with multiple y's, and vice versa. Okay, then we're going to start solving for y. There's only going to be one y that we have to solve for anyways. And once we get y by itself, we're going to replace it with f inverse of x, right? Because we started with f of x, we want to end up with the inverse. We denote inverse with that little -1. Okay, so let's do that process out real quick. So first step, it says replace f of x with y. So in our function, here we see f of x. We're going to replace that with a y. We're going to keep all the rest of the stuff the way it is. So we've got y equals 7x minus 3. Step 2 says to replace all x's and y's. So here I have a y, it should become an x. Here I have a x, it needs to become a y. So we've taken care of step 2. Step 3, we're going to solve for y. This takes a little bit of effort. Right? I need to get rid of the stuff surrounding y. First that's going to go is the 3. We're going to add 3 to both sides. So we have x plus 3 equals 7y. In order to get rid of that 7, we need to divide. What we end up with is y equaling x plus 3 over 7. But our last step says to replace y with f inverse of x. So I'm going to do that. Right? Here's my y. We're going to replace that with f inverse of x. A little bit off the screen here. Okay, the rest of the function is what we solved for. That's part of our solution. So x plus 3 divided by 7. And there's our inverse. Okay, we're going to do the same thing with this next problem over. First step, we said we want to replace f of x with y. So here we have y equals x minus 5 divided by 2. Second step says switch all x's and y's. So here our y becomes an x, and our x up here becomes a y. Step 3, solve for y. Okay, in order to solve for y from this side, we have to get rid of that 2. We're going to do that by multiplying. So we have 2x equals y minus 5. In order to get rid of that minus 5, we're going to add 5 to both sides. That goes away. That y, which is all that's left on this side, we're going to replace with f inverse. So what we have is f inverse of x. And on this side, we came up with 2x plus 5. Okay, inverses are pretty easy to do once you get the hang of them. And you're going to have 2 problems to try out on your own. Okay, so you know what to do at this point. Try them out, pause the video, check them when you're ready. Alright, let's see how you did with these. I know I've been throwing some more challenging problems at you. Hopefully it's not throwing you off too much. Right, we know we have to substitute y to begin with. What we're thinking about after we switch is how can I get rid of the things that are happening to y. Right now y is being rooted, right? We have the root of y plus 4. So to undo that, we have to square. And I'm going to do that to both sides. What we have now is x squared equals y plus 4. All we have to do now is subtract 4 from both sides, and we've got y all by itself. And we're just going to switch y to f inverse. What we came up with here was x squared minus 4. That was the trickier of the two. This one over here, we know we take y and replace it. Second step, we know we're going to switch all of our x's and y's. Now when we start solving for y, first thing that's going to go is that divided by 3. We get rid of that by multiplying. So we have 3x equals 2y minus 1. Next thing that's got to go is the minus 1. We get rid of that by adding 1 to both sides. So we have now 3x plus 1 equals 2y. To get rid of the 2, we divide by 2. Okay, now I've got my y isolated. I'm going to change that to my f inverse. Actually, I'm sorry, this should be g inverse for this particular function. Okay, and what we have left with over here, we have 3x plus 1 divided by 2. I'm sure that you came up with those same solutions. Alright, we only have one more thing to go over as far as inverse functions go. And that's checking if two functions are inverses of each other. Okay, so here we go. What it tells us here is that if two functions f of x and g of x are inverses of each other, then f evaluated at g and g evaluated at f will both result in x. Okay, so pretty simple. We're going to plug one into the other, and it's going to give us x out for both. If we don't get just plain old x out, then one's not an inverse of the other. Okay, pretty simple. So let's start with the first problem, right? They give us f of x as 5x minus 3, and g of x is x plus 3 over 5. We want to check to see if they're inverses. So to start, I'm going to evaluate f at g, which is x plus 3 over 5. That means I'm going to plug in that expression anywhere I see an x. So here we have 5 times x plus 3 over 5, all minus 3. And here's where you're going to start seeing stuff eliminate and hopefully get to just an x, right? I have 5 multiplying this thing, which is divided by 5. So these are inverses. Those will eliminate. Now what I have is x plus 3 minus 3, and I can see that my 3's are going to eliminate, and I'm left with plain old x. So far, so good. What I need to do now is evaluate g at f. So evaluate g at 5x minus 3. So I'm going to plug that in up here, right? 5x minus 3 plus 3 divided by 5. My 3's are going to start off by canceling, which gives me 5x divided by 5. Now I can see my 5's end up canceling. I'm left with just an x. So we plugged in, right? We evaluated both functions, and we came up with x for both. So we would see, yes, these are inverses. Or I guess they were saying prove that they're inverses, so we just proved it. Okay, this time they're asking if they're inverses. So we're doing the same thing. And if we come up with x for both of them, then yeah, they're inverses. If we come up with something that's not, then they're not inverses. So let's check. If I evaluate f at g, which is x squared minus 5, I need to do x squared minus 5 minus 5 all under the radical. Right here we end up with square root of x squared minus 10. That does not simplify any further, and I should notice that we don't end up with just plain old x. There's nothing else to do in this problem. We didn't come up with x as a solution, so it's clearly not an inverse. So they are not inverses. I don't even have to check g of f because I want them to both be inverses of each other. Clearly, it didn't work for that one. Okay, so you've got two problems to try on your own. The first one is asking you to prove, so you're going to make sure that they both end up with x. Second one is asking you if they're inverses, so there you'd have to check to see if they both equal x. So try them out, pause the video, and resume when you're ready to check your solutions. Alright, let's see how you did. We're going to evaluate f at x plus 6 over 2, which is g's function. So what we have is 2 times x plus 6 over 2 minus 6. We're going to see our 2's eliminating each other right away. Then we're going to see our 6's eliminating each other, leaving us with just y. Then we need to check g, evaluated at f. So if we substitute here, we get 2x minus 6 plus 6 divided by 2. We notice our 6's right away. They're going to cancel each other. Okay, leaving us with 2x divided by 2. Those 2's eliminate, and we came up with x as well. So we just proved that g and f are inverses. Second problem, they're asking if they're inverses. So I need to start off by evaluating f at g. Okay, so if I plug in, that means I have x squared plus 1 minus 1 under the radical. I'm going to notice my 1's eliminating. And then I have the square and the root, which cancel each other out, and I'm left with just plain old x. Now if I do g, evaluated at x, here I'm going to have square root of x minus 1 squared plus 1. The square root and the square are going to eliminate, and I'm going to be left with x minus 1 plus 1. My negative and positive ones eliminate each other, and I'm left with just x. So now I check. I got x's for both. That means yes, this is in fact an inverse. So that's it for this particular lesson. I know it was another long one, but we went over a couple of things, right? Even functions, which are symmetric about the y-axis, we check if f of negative x is equal to f of x. We had odd functions, which are symmetric about the origin, right? We checked to see if the opposite of f was equal to f evaluated at the opposite of x. And last, we had inverses, in which case we evaluated each function and checked to see if we got x as a result. Alright, if you have any questions, leave them in the comments or bring them with you to class, and we'll talk about them there.